problem set 24. This one's pretty much all integrals. So that's fun. Let's go ahead and take a look at number 1 here. It looks pretty straightforward. So we just want to evaluate that indefinite integral there. So that looks, in case that's a little unclear, that looks something like this. And in this case, we just want to be undoing that power rule. So I know normally I would subtract 1 from this exponent and put this exponent down in front. So I'm going to do the exact opposite. I'm going to add 1 to that exponent. So it's going to be x to the 8th. And since I would normally put that 8 in front, I'm going to take whatever coefficient this has. In that case, it's 1, and divide it by that. Next up, this over here, I said it's a minus sign. Again, add 1 to this exponent. 7 plus 4 is 11, I believe. 11. So it's going to be x to the 11/7. And this time, normally I would put this in front, so I'm going to divide by this, which is the same as multiplying by 7/11. But I also have this coefficient in front, so it's going to be that, which is then going to be 14/11 right there. And then, of course, I have plus pi over 2. Well, in order for this to be here, there must have been an x there prior. So I'm just going to write it like that. And then, of course, plus c for any potential constants that were there before that derivative was taken. And that's all there is to that one. Like I said, that one's pretty straightforward. And since it's an indefinite integral, we don't actually have to evaluate anything. Let's keep going. Let's take a look at the next one. This one's got some trig involved, so that's fun. So that integral, again, in case that's unclear, looks something like this. And because there's this minus sign here, I can take the integral of these separately and then put them back together. So this one is just simple power rule. So that's going to become a 3, and then I'm going to divide by 3, so that becomes 2 divided by 3 x cubed. That's nice and straightforward. This here, however, ignoring this coefficient, because that doesn't actually matter, let's see, the integral of cosecant squared of x. Well, we got to think back to our known trig derivative. So I know, of course, the derivative of cosecant of x is going to be a negative cosecant cotangent. But then maybe the derivative of cotangent is going to be a negative cosecant squared. That looks about right, and we do actually have this negative in front, so I can kind of factor that in there. And then there's just this 4 in front, so it's going to be a 4 cotangent x. And then again, because this is an indefinite integral, don't forget that plus c. And boom. Oops. Okay. Moving down to number 3, we've got 4 plus 3 divided by x squared. I'm going to take the integral of that. Obviously, because of this exponent here, I can't just take the integral, so I want to kind of multiply this out. So I'm going to do that over here. This isn't too bad, so it's squared, so it's just multiplied by itself. Let me just kind of do that FOIL. So it's going to be 16 plus 12 over x plus 12 over x plus 9 over x squared. So it's going to be the integral, and I'm going to reorder this. So that's 9 over x squared. Or I could think of that as 9 times x to the negative second power. This is going to be 24 over x when I combine those. So plus 24 over x plus 16. Okay. Let me just erase some of that up there, get it out of our way. Now, and this is pretty straightforward because it's just undoing that power rule. Oops, and it's not undoing the things that I'm Okay, well that's frustrating. Okay, what was it? It was 9 over x squared plus 24 over x plus 16, I believe. Oh, and I rewrote that 9 over x squared as a 9 times x to the negative second. That's pretty easy because that's just undoing that power rule again. So that's going to be adding 1 makes that a negative 1 or 1 over x. And then because it's that negative exponent, I'm going to divide by that negative 1. So this becomes negative, so it becomes a negative 9 over x. So negative 9 over x. And then our next piece, we can't consider it the same way because that would end up getting us an x to the power of 0, which is just 1, and that doesn't make sense. So instead we have to recognize that 1 over x is the derivative of natural log of x. It's just something we need to memorize. And then of course this is a coefficient in front, so it's 24 times that. So the integral of this is going to be 24 natural log of x. And then of course the integral of 16 is just going to be 16x and plus c. It won't let me write that because where it is. Plus c. And that's all there is there. Natural log x plus c. Okay. This next one is a definite integral. It's a little bit more tricky for us. I'm going to go ahead and erase this again. So now we've got from 4 to 9. We've got this squared. It's another squared, so we're going to want to distribute that. This one's a little bit different because it has 3 terms, but that shouldn't be too big of an issue. I don't think I actually meant to put that plus 1 there. We're going to actually pretend that that doesn't exist because I don't feel like it's necessary for this problem. Let's just keep it a binomial. Okay, and again, I'm going to have this, and it's squared, so set up all that. And then, of course, let me FOIL. That's obviously going to be positive, and it's going to be positive x, so it's just x. Then that's going to be positive, and that's going to be 2 square roots of x over square roots of x, which that cancels, so that's just 2. This is going to be the same thing, so it's going to be a 2 plus a 2, which is a 4. And then it's these multiplied, so it's going to be positive, and it's going to be positive 4 over x. Okay, and that's a lot easier to work with now, right? Because the integral of that x is just going to be 1/2 x squared, because we're undoing that power rule, plus 4x plus 4 natural log of x, because, right? And I'm not going to put that plus c here because it is a definite integral, so now I want to evaluate all of this on those bounds. We're going to come right down here to do that. So for this, I just plug in my upper bound, so it's going to be 9 squared is 81 over 2 plus 36 plus 4 natural log of 9. And then I subtract our lower bound plugged in, so it's going to be minus 4 squared is 16, 16 over 2 is 8. And then also minus, because we're distributing that negative, minus 16 minus 4 natural log of 4. And that's going to get us, this is a negative 24. And taking those together, that's just going to be 12 plus 40.5 is going to be 52.5, and then plus those natural logs there. Okay. And we can just leave it like that. You're welcome to plug that into a calculator if you so please. But yeah, I'm just going to leave it like that. Or, actually, I could technically simplify that by combining these natural logs, because remember, subtracting a natural log is the same thing as dividing their insides, and this is, let's see, so ignoring this part, that's 4 natural log 9 minus natural log 4 to the 4th, so I could consider that 4 natural log 9 minus natural log of, let's see, I think that's 256, which is then 4 natural log 9 divided by 256. There we go. And that's probably as simplified as that can be. So that's how we'll leave it. Next up, we have number 5 here. This is another trig one. Let's take a look here. So we've got negative cosecant of x times, in parentheses, a positive cosecant of x minus the cotangent of x. First thing we have to do is distribute that negative cosecant. So it's going to be negative cosecant squared of x plus cosecant x cotangent x. Okay, and I know the integral of a negative cosecant squared is just cotangent. And I know the integral of this, well, the integral of a negative version of this is going to be cosecant x, but because this is positive, our integral has to be negative. So there's our integral. We have to evaluate it on these bounds. Reminder that cosecant of x is the same as 1 over sine of x, and cotangent of x is the same as cosine over sine. So evaluating this, it's going to be cotangent of pi over 2, which is the same as cosine of pi over 2 over sine of pi over 2, and then minus cosecant of pi over 2, which is then 1 over sine of pi over 2. And then we're going to subtract this with that plugged in, so it's going to be minus cotangent of pi over 4, which is then this. And then minus this part as well, but those cancel out, so it turns into a plus. Okay. Obviously, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this is 0 over 1, or just 0. Sine of pi over 2 is 1. So this is 1 over 1. So that's minus 1. Cosine of pi over 4 is square root of 2 over 2, as is sine of pi over 4. So if I divide that, that's just going to be a 1. And then 1 over sine of pi over 4, so that's 1 over square root of 2 over 2, which is then just 2 over square root of 2, which I believe simplifies to just square root of 2. So this is plus square root of 2. So we get negative 2 plus the square root of 2. And I don't know exactly what that is. You're welcome to plug that into your calculator. Okay. Number 6 is a fun one just because it's an absolute value. So we get from negative 4 to 2. We have this absolute value of x plus 1. Okay, and so again, if we want to take the integral of an absolute value function, we want to split it up into 2 integrals, which we can do with that addition property, right? So first we need to see when it kind of flips, right? So set this equal to 0. What is my x value going to be for this to be equal to 0? Well, that's obviously going to be when x equals negative 1. Now, if I go further in the negatives, is my inside of my absolute value going to be negative or positive? If x is negative 2, that makes this whole thing negative 1, which is then 1, which means that from negative 4 to negative 1, it's going to be negative whatever's inside these parentheses. And then from negative 1 up to the rest of that, right, any positive values, it's just going to be whatever's in that parentheses, right, because there's no need for the absolute value there. So that's how we kind of split up that integral, and otherwise it's just a normal integral. Of course, I can distribute that negative, so it's going to be a negative x minus 1 is how I could write that. So negative x minus 1, which just makes that integral a little bit easier. So then that's going to be negative 1/2 x squared minus x on these bounds plus 1/2 x squared plus x on these bounds. Okay, plug in that negative 1, that's going to be 1, so it's going to be negative 1/2 plus 1, and then of course minus this. That's going to be 16. Negative 16 over 2 is negative 8. Minus the negative turns into a plus 8. And then negative 4. That's going to be positive 4, but we're still subtracting. And then plus whatever we evaluate this to be. So let's plug that in. That's going to be 4/2 is going to be 2 plus 2 minus 1/2 minus negative 1. So then that turns into, well, it's a 1/2 plus 4 plus 4 plus 1/2, which is then 9. So that equals 9. Okay, making our way down. We're a little more than halfway through now. Going on to number 7, it's another absolute value function, but this one's just a little bit different. So we want to evaluate the integral of f of x, which is this function. Okay. And again, we're going to split it up, and this minus 1 doesn't change anything. We're going to split it up based on that absolute value there, because that's what really matters. So I want to know, again, I want to set this equal to 0, so it's going to be x cubed plus 27 equals 0. Well, that's going to look something like this. So now x has to be negative 3 for that to equal 0. And of course, if I go further in the negatives, this interior is negative. So again, I'm going to split this up like so. And that tells me that that needs to be a negative x cubed plus 27 minus 1 dx, which I could then distribute that negative. So it's just negative x cubed minus 27 minus 1. Oh, and I can actually combine those to that. There we go. And then, of course, plus the other side of that, which is just x cubed plus 27 minus 1, which is then x cubed plus 26. Okay. Now, of course, again, we just evaluate it. So then that's going to be negative 1/4 x to the 4th minus 28x on these bounds plus 1/4 x to the 4th plus 26x on these bounds. Okay, and we're going to get some big numbers here just because this is an x to the 4th. Let's see, I know 3 to the 3rd is 27, 3 to the 4th is 81. I know 6 squared is 36. Oh, I don't actually know beyond that off the top of my head, so give me one moment. So 36 times 36 should be 6 to the 4th. 18, 21, 18, 9, 10. And I'm just gonna double check that with my calculator, just make sure I didn't screw up. Nope, that's good. Okay. So then 6 to the 4th is 1,296. Okay. So then coming over here, plugging in that negative 3, and that x to the 4th turns it positive, so it's going to be, well, but there's still that negative, so it's negative 81 over 4. And then, 28 times 3, I know it's 56 plus 28 is 84. So it's going to be plus 84. Then minus a negative is plus. That's going to be that, which we can definitely reduce a little bit, but I won't worry about it right now. And that turns into a plus, but we're subtracting 28 times 6. That's going to be double that 84, so it's going to be 168. Like I said, pretty big numbers here. And then plus, we evaluate this, obviously plugging in a 0, that's all 0. And then subtracting that plugged in, so it's going to be, that's negative because we're subtracting. And then that's going to be negative plugging in negative, but it becomes positive because we're subtracting. Positive 26 plus 3, that's going to be 78. I think 78. So it's going to be 60. I need to, yep, okay. And now we just combine all of this. So, oof, big numbers, big numbers. Let's see, 1296 divided by 4, and 12, that's going to be 3, and then 96 divided by 4 is something that I should know. There we go. Did I say divided by 3? Divided by 4. Hold on. Oops. This should be 24, I think. I'm going to double check that. I should not just trust myself to do that in my head. Oh, that's right though. Okay. Okay, so this is the same as just 324. So I'm just gonna toss that in. Okay, well, fun. I know 168, well, negative 168 plus 78, that's gonna be a negative 90. So minus 90. I know these added together, it's going to be 408. And then I've got these there. If I add those together, it's going to be minus this. Okay, 408 minus 90. Well, 400 minus 90 would be 310. So 318, I think. Minus 40 and a half. That's harder for me to do in my head. Okay, and then minus a half, so it's going to be 277 and a half. And that was quite a bit. But we are almost done. Just 3 more questions. And they should not take too long. Number 8 down here, we've got from 0 to pi over 4. Take the integral of tangent squared x plus 1, which this one is special because that's actually one of our trig identities. We don't just know the integral of a tangent squared x based on what we've learned so far. However, if we know our trig identities pretty well, we'll recognize that this is the same as secant squared, which we do know the integral of secant squared because I know that the derivative of tangent is secant squared. So this whole thing is equal to secant squared. So it's actually the integral of secant squared of x, which is then just tangent of x on these bounds. Remember that tangent is sine over cosine. So that's going to be sine of pi over 4 over cosine of pi over 4 minus sine of 0 over cosine of 0. This is going to be 1, and this is going to be 0. So our answer is just 1. Number 9 is one that might look a little intimidating, but it's surprisingly easy. So there's a lot happening here, obviously. And what's happening here is we're taking the integral of a derivative. And what that means is, well, because these are opposites, right, our integral is the antiderivative. So we're taking the antiderivative of a derivative. So these parts cancel out, and we're actually just going to have this. because we still do have to evaluate it on those bounds. So I'm going to plug in cosine of pi. I know cosine of pi is, well, I won't worry about that right now, actually. And then minus cosine to the 9th of 0. Minus 3, but we're subtracting that whole thing, so it becomes positive. So I know cosine of pi is -1. So -1 to the 9th is -1. Minus 3 minus cosine of 0 is a +1. 1 to the 9th is obviously 1, but we're subtracting. And then I see these parts cancel out, and I just have -2 because I combine like terms. And finally, this last question we have to use a calculator for. So it wants us to approximate this integral using a left Riemann sum with 25 subintervals of equal length. We want to round to the nearest hundredth. So once again, I went over it in my other videos, though I do think I made a mistake in one of them, so I want us to be careful here. So what we've got to do here is, first of all, I know we're going from 0 to 1, which means that the distance between them, my subintervals, are going to be of size 1/25, because I'm just going to divide that space by 25. So if we remember those steps on the calculator, we go to second, stat, and then math, and then sum, and then we do that again. We do second, stat, and this time ops or operations, and this time we're going to go to sequence. And again, it's going to ask us first, that first little prompt, this part here, we're going to plug in this function. So it's going to be the square root of 1 minus sine of x. Careful with your parentheses here. So that's 1 minus sine of x. Our variable is obviously x. Our start, well, it's a left Riemann sum, so we're going to start all the way at our lowest value. So our start is going to be that 0. Our end, because it's a left Riemann sum, we don't quite include that last that last point, really. So we're not going to include 1, but we're going to go all the way up to 1/25th away from it. So it's going to be 24/25. 24/25, and our step in this case is going to be 1/25, as we previously established. And then we just press paste and enter. And that gets me 18 point something, but that is not my answer yet, because all that gives me is the sum of like the heights on my graph, right? So if our function was, say, something like sine of x, and it was like this, doing that would just give me like all of these heights, but it wouldn't give me the areas because I'm not multiplying by this distance, if that makes sense. We just have the heights and I need to multiply. So in this case, we have to multiply by that distance. And of course, the size of our subintervals is that 1/25th. So I'm going to multiply my answer by 1/25th. And our actual answer looks something like this. It's obviously a much longer decimal, but the question prompts us to round to the nearest hundredth, so that is that. Oops. That is our last question for this problem set. So I hope that this was helpful. I hope that this was easy to understand, and I very sincerely apologize if I messed up on instructions for using the calculator in one of my previous videos, as I think I may have. Yeah, I hope this was helpful, and thank you very much for watching.